Thank you, George. Good afternoon, everyone. Let's adjust this. There we go. Okay. Wow, a big room. Okay, so thank you for sticking around this afternoon to hear my presentation. As George said, I'm from Life Technologies, and I'm responsible for the Open Array system, and QuantStudio Real-Time PCR. So in this presentation, I'd just like to give you an overview, really, of what this technology is and how it can be applied to your research. So as you know, Life Technologies is a huge company, and in fact we develop and manufacture a wide range of genetic and cellular analysis tools, everything from reagents to benchtop devices to high-end instrumentation that can help researchers like yourselves answer those big questions of plant biology to help better understand how plants work and how we can make plants work for us to improve humankind and our environment. And essentially, Life Technologies' genetic analysis division, from which I belong to, has essentially got expertise in two areas, sequencing and QPCR. And as you'll hear from my colleague Justin Lee in the presentation after this, we're making quite a big impact in the field of next-generation sequencing using the ION technology. However, we're also making inroads in the field of QPCR. And I belong to an area of research involved in next-generation QPCR. And essentially what we mean by these next-generation platforms is we're essentially improving productivity whilst at the same time driving down cost. Now, with next-generation sequencing, I'm sure you're all familiar, there's been some fantastic developments, namely the ION chip, and also other platforms like Illumina and Roche. However, QPCR is a slightly different game. And the way we've effectively achieved this with QPCR is to miniaturize the reactions from microliter scale down to nanoliter scale. So the majority of this presentation will be spent with me explaining what the technology is behind nanoliter QPCR, and that's the Open Array plate. I'll then explain how the Open Array plate can be used to plant researchers such as yourself. Now, the main application of Open Array technology is in marker-assisted selection. However, you can also apply this technology to the areas of high-throughput gene expression for profiling pathway analysis, and also the area of digital PCR. Now, digital is a very big subject, and unfortunately I don't have enough time to talk about it today, but essentially what we're doing with digital is we're taking qPCR to the next level of performance. And it has some nice niche applications in the detection of rare contaminants or GMO alleles. And I'll briefly explain those applications towards the end. So without further ado, the Open Array plate is essentially a stainless steel plate the size of a microscope slide. And within that plate are 3,072 holes, within which we trap 33 nanoliter qPCR reactions. Now you can see the plate behind me here. It looks a bit like a microarray chip. So the plate itself is divided into those little squares. Those squares are called subarrays, and each subarray has 64 through holes. And the reason we divide the plate like this is it allows us to achieve a flexible range of assays to samples. In other words, we can screen a small number of assays per sample all the way up to a large number of assays per sample by using or combining various parts of the plate. And the way it works is very simple. Essentially what we do is we treat the plate and render the top and bottom hydrophobic. However, we maintain the interior of those through holes hydrophilic. And what this does is it allows us to load the plate with qPCR reactions purely by capillary action, rather than having to very precisely measure 33 nanoliters, because as I'm sure you'll agree, it would be impossible to do that. So what we actually do is we spot TACMAN genotyping or gene expression assays into the through holes using a robot. And then you as the user actually apply the sample in your laboratory using a capillary robot. So essentially what this achieves is it means we can spot different assays into neighboring through holes at manufacture, and then the sampling is performed with a much lower level of precision using robotics that come with the instrument. The instrument that runs the Open Array plate is called QuantStudio 12K Flex. It's our flagship real-time instrument. And in fact, it's not just designed for high-throughput applications on Open Array. It's a very versatile instrument that can perform both high-throughput and everyday low-throughput QPCR. So the workflow looks like this. You start by selecting which assays you want to screen. So you'll be mainly interested, I guess, in SNPs. So you'll be designing TaqMan SNP genotype assays, or alternatively, you can use TaqMan gene expression assays with this system. And they are spotted into the through holes of the Open Array plate and dried in place with a polyethylene glycol matrix so that they're stable. And they're made in a batch and then shipped to you for your project. Then when you come ready to use the plates, you use an accessory robot called AccuFill. And AccuFill's job is to load your sample, so for SNP genotyping, that's genomic DNA, or for gene expression, cDNA, in master mix and loads that to the Open Array plate. The Open Array plates are then placed in the QuantStudio instrument, thermal cycled, and then you detect the results. And I've got a short video here to explain how AccuFill works. Hopefully I can get this to work. No, it won't work. There we go, let's try that. Please work. Wonders of technology, eh? Okay, I guess the video doesn't work. Oh well. Basically, to summarize what the video would have shown you, essentially what AccuFill does is it takes your samples from a 384-well plate and then it applies it to the Open Array plate. It takes about 30 seconds and involves purely capillary action. Now, the virtue of this is it minimizes handling time and it minimizes the exposure time of the plates to the environment, which could lead to contamination. Needless to say, you can load an Open Array plate of over 3,000 33 nanoliter qPCR reactions in less than 30 seconds. So it's a very easy system to use. Once the Open Array plate is loaded, you simply have to seal it with a plastic lid using this clamp device. And then you inject a substance called fluorinert, which acts like good old-fashioned mineral oil. And that prevents the 33 nanoliter reactions from evaporating. You seal the plate with a plug, and then you're ready to do your qPCR. So the QuantStudio will accept 4 Open Array plates at a time, and you can turn around over 36,000 genotypes in a single working day. So now I'll explain how we use the Open Array technology for marker-assisted selection. So as you're probably all aware, the virtues of marker-assisted selection have greatly accelerated the rate at which we can develop much better crops, combining multiple desirable traits to help us meet demand of a global need for greater amount of food with lower economic burden. So things such as yield and resistance to biotic and abiotic stresses can be combined using marker-assisted selection technology. Now, traditionally, people have used SSRs as markers for these traits. And SSRs have been very useful. They're highly valuable because of their multi-allelic properties. So you need relatively few SSRs to track your traits of interest. However, the downside of using SSRs is that they're rather laborious to monitor and not really amenable to high throughput. So when it comes to complex marker-assisted selection, where you need to monitor several traits simultaneously, it becomes quite difficult to do this using SSR markers. As a result, people have switched to the use of single nucleotide polymorphisms as a marker. Now, the advantage of SNPs is that they're very easy to score and very amenable to high throughput screening. Furthermore, using TaqMan technology, you can achieve very high specificity. However, the downside of SNPs is that they are biallelic. Therefore, you need relatively more SNPs than SSRs to achieve the same level of genetic information. Therefore, to employ this for marker-assisted selection, you need to have a system that can manage a high level of SNPs from a large number of samples simultaneously. And to date, there's been relatively few platforms that can achieve this. This is exactly where the Open Array plate comes in as one of the main applications of this technology. So with the Open Array plate, we can screen anything from 16 to 256 SNPs per sample. As you can see in this diagram, essentially what we do is we either split the subarrays or combine them per sample to achieve lower or higher levels of complexity. So anything from simple trait selection with just a small number of markers could, for example, be fitted on the format 16 plate, all the way up to complex trait selection where we have a larger number of SNP markers. We can use a higher format plate, such as the format 192 or format 256. And using this technology, we can screen hundreds or even thousands of samples per day with a very low cost per data point of anything from around 10 to 20 cents per SNP. And in the past, we've been very successful with approaching AgBio companies for the use of Open Array in marker-assisted selection. Unfortunately, a lot of these situations are commercially sensitive, so I'm not able to show you the data that they produced. Needless to say, we've successfully genotyped crops such as maize, tomato, soybean, cotton, using the Open Array platform. And part of the reason I'm here today really is to reach out to the rice research community to see if there's any projects which you may have which may be suitable to the Open Array format. And rather than just design these technologies and put them out on the market and hope for the best, Life Technologies is a company that likes to collaborate with researchers. So we like to take your ideas and get them working using our technology. So if there is anyone out there that's interested in discussing more about this, I'll be happy to talk to you afterwards. So to summarize then, what Open Array SNP genotype gives you is a much lower cost per reaction than microliter qPCR. As I just mentioned, anything from around 10 to 20 cents per SNP is realistic with this technology, as opposed to 50 cents to $1 using, say, a 5 or 20 microliter standard qPCR reaction. So it's highly amenable to complex marker-assisted selection programs. Furthermore, we use TaqMan chemistry, and as many of you will be aware, TaqMan is considered the gold standard for SNP genotyping, giving the highest quality call rates possible using qPCR methodologies. Of course, the throughput is very high. We're typically looking at projects in excess of 10,000 data points. So you need to be really looking at thousands of samples to screen using the Open Array plate. With this high throughput and high automation, there's less probability for error because there's less manual handling steps. Furthermore, there's no need for additional robotics. Everything is handled by the AccuFill and QuantStudio systems. And of course, this can all be achieved in much less time. Typically, you can complete projects in excess of 100,000 data points in less than a week. So this is greatly going to accelerate your research. And as you'll hear from my colleague Justin Lee, who's due to present this afternoon as well, QuantStudio is not just a standalone instrument. In fact, Life Technologies produces what we like to think of as complete solutions. Now, QuantStudio is a fantastic instrument for marker-assisted selection. You can also use it to validate novel biomarkers that have been identified downstream of next-gen sequencing. And as you'll hear from Justin, the new ion proton next-generation sequencer is revolutionizing the way that we can discover new biomarkers in plant species. So that's the main application, really, of Open Array for plant research. But I'd just like to spend the last 5 to 10 minutes of this presentation explaining to you how else we can use this high-throughput nanoliter scale qPCR technology. And the first of these is high-throughput gene expression. And the application of Open Array in gene expression work is to be able to profile a large number of genes simultaneously from a large number of samples. So this is great for doing basic research into pathway analysis. The final application is digital PCR. And with this application, as I mentioned earlier, we're pushing the performance of standard qPCR in terms of sensitivity and precision. And that has some niche applications in rare contaminant detection or GMO detection. So let's start with the standard gene expression. Essentially what we're looking at with the Open Array plate is we're taking the high content capability of a microarray chip, but we're combining that with the high performance characteristics of TaqMan QPCR. So what we're able to do with this plate is essentially screen anything from 18 to 224 genes from each sample. Furthermore, we can achieve a much higher sample throughput than can be achieved with standard microarray technology, in fact in excess of 800 samples per day. Another great feature of using TaqMan as opposed to hybridization technology is that we can get a much broader dynamic range, typically up to 7 logs of dynamic range compared to the 2 to 3 that you might expect to achieve with a microarray system. And TaqMan is regarded as the gold standard purely because of its high specificity. The fact that we're using TaqMan probes specific to your genes of interest allows you to eliminate false positives. All this combined with a much easier workflow and a much lower cost than other technologies. So as I say, TaqMan Open Array gene expression is ideal for pathway analysis, typically for large studies where you're looking at hundreds of samples simultaneously. And just to give you a quick example, only last week I was in Adelaide in Australia meeting with a new QuantStudio customer who's recently purchased this platform specifically for pathway analysis in plants. And they'll be looking to look at around about 100 to 150 genes across 3 to 4 different species of plant, namely wheat, soy, and maize. And they're looking to do around 1,000 to 2,000 samples at a time. So, of course, they're very excited to get on board with this technology, and they should be starting this work sometime early next year. However, you may not have such a grand-scale project, you might be thinking, maybe only less than 100 samples. And for this situation, we can do a similar kind of approach, but not using the Open Array platform, instead using something called a TaqMan Array card. Now, the TaqMan Array card is a kind of go-between format between a 384-well plate and the Open Array plate. It's a microfluidic card, and it contains 384 chambers. Each chamber holds a 1 microliter qPCR gene expression assay. So you can analyze anything from 12 to 384 genes against 1 to 8 samples at a time per card. So typically tens to maybe less than 100 samples can be screened quite comfortably with the TaqMan Array card. And these can also be run on the same instrument. They run on the on the QuantStudio 12K Flex instrument. The final application, just in the last 5 minutes, I'd like to introduce to you is digital PCR. And I understand that digital PCR is a relatively new concept for many people, so I'm just going to take a few minutes to explain what it is and how it works. And digital PCR is really revolutionizing the way people are looking to detect GMO or contamination from non-specific alleles in seed batches. And digital PCR essentially is the most sensitive, specific, and precise way for quantifying nucleic acids. It allows you to achieve a performance that cannot be achieved with standard qPCR. Essentially what we're doing is we're counting molecules. It's a method of absolute quantitation. This is in contrast to standard qPCR, which is essentially relative quantitation. You're taking your sample and you're generating a CT value based on the quantity that was present. And you're comparing that to a reference gene or known standards. So that's your relative quantitation. Now with digital PCR, there are no reference standards. We're simply counting molecules. And furthermore, it's independent of a lot of the weaknesses that plague qPCR, namely assay efficiency, instrument calibration, and also the efficiency of the reaction. And it relies on the method of single molecule detection. So with digital PCR, what we're doing is we're taking our sample and diluting it down to a concentration where we would expect either 0 or 1 copy per replicate. And we perform hundreds or even thousands of replicates of the same reaction. So these reactions are distributed across the Open Array plate because they can achieve very high content. You then perform real-time PCR on those replicates, And where there was a single molecule, you'll get amplification, or you'll get a signal. Where there is no molecule present, you'll get no amplification. And all the digital PCR software does is count the ratio of positive to negative reactions. Then by adjusting this back through a dilution factor, we can calculate the concentration of your target molecule in the original sample in terms of copies per microliter. Of course, being able to detect and quantify a sample in terms of copies per microliter is a lot more standardizable from laboratory to laboratory than, for example, a delta-delta CT value. And why is this great for detecting rare alleles or GMO contamination? Well, essentially, when you try to do this using qPCR, it's rather difficult because that rare target is present at a very low abundance compared to the wild type. So when you amplify it by qPCR, that rare target appears with a very, very late CT value. And it can be sometimes difficult to discriminate that late CT value from true and false positives. However, with digital PCR, what you're doing is you're taking all the molecules in the sample and separating them out into individual compartments, so that even a low abundance target amplifies with equal intensity to the wild type background target. And this makes it much, much easier to quantify as a true positive. So with the Open Array technology, what you're doing is taking your sample and you're diluting it down in master mix to the appropriate concentration where you would expect around 0 or 1 copy per 33 nanoliter replicate. You distribute that across the Open Array plate using the AccuFill system. You then thermal cycle in the QuantStudio. And the digital PCR software does all the calculations for you. So it'll count all the positives to negatives on the Open Array plate and give you your answer in terms of copies per microliter. I just want to end with a quick example of how we've successfully applied this to the world of seed batch quality control testing. However, you can use this for almost any application where you have a rare target that's present in a background that you need to discriminate against. So this was a proof of concept collaboration with a major ag bio company in Canada. And they wanted to explore digital PCR to see if they could see any increase in sensitivity from their existing method for seed batch quality control testing. Now, their existing method was able to detect down to a 1% sensitivity. And they wanted to see if digital could improve on that. So they selected 7 SNP alleles that they wanted to discriminate and engaged us for a proof of concept study on the Open Array plate. Now, in this study, essentially what we did is we took that background wild-type DNA and we spiked in the contaminant DNA at a range of different concentrations, all the way down to a 1 in 10,000 or 0.01% concentration. And what this image behind me shows is the actual raw data from the Open Array plate. So where you see those little red squares, that's a positive amplification, and the black squares are where there's negative amplification. And on the left side of the plate is where we spiked in the GMO targets at 0.01% and tested those using an assay specific to the GMO alleles. By contrast, on the right side of the plate is the same experiment, but using the assay specific to the wild-type alleles. You can see, using this data, that we've been able to detect a 0.01% sensitivity using 1,280 replicates of the Open Array plate. So this is a 100-fold improvement on their existing methods. The customers were very happy with the data and be looking to employ Open Array for their routine seed QC testing. So to summarize then, essentially the QuantStudio is an all-in-one real-time system. It does your low-throughput qPCR, everyday reactions such as assay validation. It also does high-throughput qPCR. And specifically, these are applications using the Open Array plate for high-throughput genotyping in marker-assisted selection or high-throughput gene expression for profiling pathways. Furthermore, it can do ultra-high-performance qPCR in the form of digital. And this is great for detecting low concentrations of contaminant or GMO. And it's an excellent complement to the whole genetic analysis workflow. As you'll hear from my colleague Justin in the next presentation, this is designed for those downstream studies post next generation sequencing, for validating SNPs of interest and deploying them for selective breeding programs. So we like to welcome any collaborations, not only to test the high throughput genotype applications, but anything involving gene expression or digital PCR. We're very keen to engage researchers in the rice community, and as you've seen, we've been successful with other crop species in the past. So we're looking forward to your input. Thank you very much for your time.